Hey everybody. So now we've got this nice collection of derivative rules, right? We've got things like our product and quotient rule, our chain rule, trig derivative, some inverse stuff, and we want to start applying this now to as close of real situations as we can come up with, right? Ultimately, that's the goal for most of us with mathematics, is we want to use math to investigate, to describe some little piece of the universe and be able to make predictions about it. And so here's a little slice of the universe, and we're going to try to use the tools that we have now to describe what's going on here and predict or understand something new about it. All right, so we've got a camera, we've got a drone rising vertically at 2 meters per second and a camera aimed at this drone. And we're told the camera is at ground level 30 meters from the launch site, and we want to know how fast the angle of the camera is changing when the drone is at a certain height, okay? So a good first step whenever we have this kind of problem, right, where a situation is described, is we got to make sure we understand this situation. And in a lot of cases, drawing a picture is the best thing to do. And I think this is certainly a case for that. So here's my ground, all right, and I've got a drone. I don't know if that looks like a drone. And our drone is rising, remember, right? So it's going up at 2 meters per second. And what do we know? We know our camera is sitting on the ground somewhere over here, all right, pointing at the drone. And we know that this camera, so if this is where the drone launched from, that this distance is 30 meters. Okay. Now, what else do we know? We know that we are interested about the angle. So I need to put something in for the angle. Let's call the angle theta. And I also want to be careful with the last piece of information, that we're interested in this angle and how it's changing when the drone is 45 meters off the ground, because I don't necessarily want to draw that 45 meters in there, because I don't want to imply that that's the height, right? The height is changing. This thing is rising. We just want to know something right at this moment it passes through 45 meters off the ground. We want to know something about that angle then. Okay, so I'll leave that off for now. We'll figure out how to put that in when we get there. So this helps me picture what's happening. Notice a few things I've done. I've named some of the things that are given in the problem. Okay, this is a big first step for any of these problems, giving symbols to the things that we want to talk about, right? I don't want to be writing the angle. I just give it a symbol. This gives us power, right? All of our algebra, we can't apply it to the world unless we give symbols, right? Algebra tells us how to manipulate symbols, so we need to give symbols to things. So we've given some symbols. We might come across things we need to add as we go, but this is a good start. So I need to start understanding what the meaning of a lot of these things are. For instance, let's start with this 2 meters per second. 2 meters per second should be setting off alarms in our head, right? We've spent this whole quarter talking about developing, this whole series of lectures, developing the idea of the derivative, right? We went through all the stuff with limits and all of these things to get at the idea of the derivative, which of course, geometrically, is the slope of the tangent line to the graph of a function at a point. Or we can think of it as, and not or, this is also, I guess I should say, because they're not different ideas, they're just different ways of seeing the same idea, the derivative, the slope of the tangent line, and the instantaneous rate of change, right? So this idea of rate of change is really, really, really intimately connected to all the ideas we've been talking about. And 2 meters per second is a rate of change. It's how the height of this drone is changing as time changes. Every time a second passes, the drone gains 2 more meters of height, okay? So that tells me a couple of things. I can think of this rate of change as a derivative. The derivative, I'm gonna call it, I'm going to talk about the rate of change of height. So I'm calling that h as time changes, right? This thing is a derivative. We don't know the thing the h function, right? Derivatives are things that are done to functions, but we know what its derivative is. The value of it is 2 meters per second, right? And I just hinted at something else. The fact that I have this derivative dh dt implies that there's a function h of t, right? The height of the drone is h of t. And so let's put that on here, right? The problem didn't tell me this exists, but I can invent this function. There's a height function for every single thing there is. If we call where I'm standing on the ground 0, right? The height of the picture on the wall over there is a function, right? At every second, it's exactly the same height. It's a boring function, but it's still a function. And so certainly for this drone, for each second that passes, we can put out, it has a height, right? So input a time, it has a height. So this height exists, and this 2 meters per second is the derivative of this height function, okay? So that's a pretty big piece of information, okay? What about the thing we're looking for? The thing we're looking for, the angle of elevation, we want to know how fast it's changing, right? Again, we want to think about derivatives. In other words, the angle changing in radians per second screams derivative. It's a rate of change. In this case, it's the rate of change. We want to know how the angle that I called theta, so that's d theta, changes as time changes. This is what we're looking for, okay? This also implies theta is a function of time. So this is our angle of elevation, right? The angle between the ground and the line of sight as drawn in this drawing, right? Again, as each second passes, you can imagine the camera is angling up to follow this drone. It has an angle, so it's a function of time. Or at least it is a function of time, and we're thinking of it that way. Okay, so I've got these two functions and these rates. One, I know what it is. One, I'm looking for. I want to know if I can use the information I have to find this rate, okay? So if I have information and I want to use it to find other information, I need to connect them somehow, right? I need to connect these things somehow. And there's a connection that I think should be jumping out at us, right? If I look at my drawing, I'll highlight it in red. There's a nice triangle sitting right here. And I'm asking a question about the angle. I'm actually asking about its derivative, but I'm going to start with just the function itself. And so I've got an angle that I'm interested in, and I've got a triangle. So trigonometry seems like an obvious place to go. So I know this height function, or I don't know this height function, sorry, but it's one of the pieces we have in play. And I know its derivative. So if I can relate the angle function and the height function, I'm in good shape. So, and I know this horizontal distance. So I've got an angle, and I know some things about the side opposite, and I know some things about the side adjacent. So a good thing to try is the tangent of theta of t is equal to h of t over 30, right? This is just the definition of tangent, the opposite side over the adjacent when we're dealing with triangles, right? Our units work out nicely. Height is in meters. That 30 is in meters, so the units cancel, and that is what we should have when we have a tangent is no units, just a number. So here's a nice relationship between the two of them, right? Well, what we're interested in is the derivative of theta. So we should try taking a derivative of this equation, right? If these are two equivalent functions, their derivatives should be equivalent. So let's take the derivative of both sides with respect to t. and see what we end up with. Okay. Now, on the left-hand side, notice what we have. I've got the tangent function, and I've put another function inside of it, chain rule, all right? So the derivative of tangent is secant squared, and we leave the inside alone. And then we multiply it by the derivative of the inside. What's the derivative of theta of t? Well, we don't know the function, but I have a symbol for the derivative of it. I called it d theta dt up here. Let's go with that for now. You can also use theta prime. I might switch to that in a moment. We'll see why. And then over here, well, the third one over 30 can come out, and I've got my dh dt. Okay. Now let's look at this equation. dh dt, we know what this is. We're told dh dt is equal to 2 meters per second. In other words, the velocity of this drone is constant, right? They're raising it up at a constant velocity. So we know that is. That piece of this equation is done. Here's what we're looking for. We want to know the value of this. Okay. So let's solve this equation for that. So we'll have d theta dt. I can divide secant squared to the other side. This is going to be equal to 1/30th dh dt. I'll have 1 over secant squared of theta, but 1 over secant squared is just cosine. So this is going to be cosine squared theta of t. Okay. So here I've got an equation for the thing that I'm looking for. Let's also put in what I just said we know. We know that dh dt is 2. So we're going to have 1/30th times 2, and we've got cosine squared theta of t. Do a little simplifying, and I've got 1/15th cosine squared theta of t. So we're closing in on what we need, or what we want, d theta dt. Okay. Let's get a little space here. We need to figure out cosine squared of theta of t. Okay. So let's look at our drawing. We didn't know we needed this in the beginning, right? But now we need it. So let's add some things. Cosine, of course, is the adjacent over the hypotenuse. So I'm gonna give this hypotenuse a name. I'm gonna call it let's just call it d, for the distance between the camera and the drone, right? And this is going to be changing, so it's also a function of time, right? As time changes and that drone gets higher, that distance looks to be increasing. So we need d of t in order to have cosine. In other words, let's write this out. Cosine of theta of t is equal to 30 meters over d of t. But we also know from the Pythagorean theorem, d of t squared is equal to 30 squared plus h of t squared, or d of t is equal to the square root of 30 squared plus h of t squared. So that means cosine of theta of t is equal to 30 meters over the square root of 30 squared plus h of t squared. All right, and the units down here are also going to be meters, because we have meters squared, and then we're taking the square root of it. So I'm just going to cancel those meters right now. Again, we're ending up with a unitless number here. Okay, so here's cosine. Here's cosine of theta. theta of t, sorry, lost my train of thought for a second there, okay? So we have an expression for cosine of theta of t. We wanted cosine squared. We're just gonna square this thing and we get 900 over 900, the square root goes away. So then we'll get 30 squared is 900 plus h of t squared, okay? Still problematic because we don't know what h of t is exactly. We don't have that function. So let's bring this back into the equation we had earlier. We have our d theta dt is equal to 1/15. We just figured out a new way to write cosine squared. And okay. All right, so here's our expression for d theta dt, right? Just substituting this thing in. Let's do a little bit of simplifying. D theta dt. So 15 into 900 should be what, 60? Yeah, 60 over 900 plus h of t squared. Here's the big, here's the last step. D theta dt depends, you can see here, depends on how high this thing is, right? And you can imagine this pretty easily, I think. When the drone launches, when it's at 0 and our angle of elevation is 0, just looking straight horizontal at it, as it rises, that angle's rising pretty quickly, right? Imagine that drone being 1,000 meters in the air and you're looking at it. If it raises another 50 meters, you barely have to tilt further, right? Just a little more tilt of your head and you're looking a lot higher, right? In other words, let's do ourselves a little sketch. If we go up 10 meters here, let's say this is a difference of 10 meters, look at how much the angle changes. But if our drone is up here and we do a difference of 10 meters, right? It doesn't take as big of a change of an angle to get that same elevation distance at what we're looking at, okay? So the rate at which theta is changing depends on the height. But we were asking about d theta dt at a particular moment, right? Remember, we wanted to know this when, precisely when the drone was 45 meters off the ground. And so we can put in a height of 45 meters. So d theta dt, so I'm going to write it this way, at a height of 45. I don't know what t is, right? I don't know what t is. I just know at some moment in time, this thing is 45 meters off the ground. And that's the moment in time I care about, right? So I don't have to see what t is to get this. And you can do some reducing. I believe this works out to be 4 over 195. And this is going to be in radians per second. Okay. So there is our rate of change, d theta dt, in this problem. Okay. So at that moment in time, for every second that passes, we get 4 195ths of a radian in elevation. And that seems to make sense to me. If I'm looking at something that's 30 meters away horizontally and then up 45 meters in the air, a change does, I don't have to tilt my head much to look a lot higher, right? I don't need a lot of radians to change my elevation much. Let's take a quick look at our units and make sure everything's working out okay here. So let's look at a few things that we have. This 1/30th, that 30 is meters, so I've got a 1 over meters. dh dt, so I'm looking right here. We have 1/30th. dh dt is meters per second, and then cosine doesn't have units, right? It spits out things that are unitless. So we're ending up with per second, right? Well, that's exactly right when you have radians. Radians is that placeholder unit where we don't actually have units, where it's just a ratio. So this is perfect in terms of units. And there it is. So we've taken this little slice of the universe, taken the information that we had, and found a way to get at this rate that we wanted. This is a particular kind of problem that people call a related rates problem, and I think it's clear why, right? We were given a rate, we wanted a rate, we figured out a way to relate them, and we used that relationship to find the rate that we wanted. And they're all different types of problems, but they follow certain patterns, right? There's certain things that we're always going to want to do. The beginning, so let's maybe make a little summary. Our related rates problems. I think the first big thing to do is understand the problem. Right, so just make sure you're reading it through and seeing what everything is. This might be a picture. Okay, this also requires us, well, let's put this as its own step. So understand is just kind of intuitively, which, oops, I think I just unshared my screen. Sorry about that. I don't know what I pressed. So understanding the problem might be a picture if that's applicable. The next big step, and maybe you could call this part of the same step, but I'm just going to put it here because I think it's so important. Introduce notation. Right? We have to name the things we're talking about. That's always one of those steps that I find students struggle with, is we can't start understanding a thing if we don't have names for it, right? You can't name too many things. If you end up naming something and you don't use it, who cares? It's just got a name. It doesn't stop you from doing the problem. In particular, look for things in the problems that are rates. And those rates imply functions, right? We saw that the speed that the drone was rising up implied that there was a function of height with relationship to time, or the fact that we were looking for the angle of elevation, how it changed with time, implied that there was a function of theta of t, right? So these rates imply functions. In other words, we see a rate, it's some dy dx, it implies y is a function of x. Okay, so you want to look for those. We're naming everything, right, that we need, but in particular, look for the rates. You're going to be looking for a rate and usually given a rate, and you want to, and then use that now to know that you have a function that rate is a derivative of. Okay. Find relationships. All right. What does this mean? Equations. Right? In what way are these rates or the functions that led to these rates related? Right? That's where we get related rates from, right? In this problem, we had a few of these, right? We started out with this tangent. We saw that we had h of t, we wanted theta of t. Tangent seemed to be a good way to relate them. Later on, we had to find another relationship because we realized we needed a cosine, which meant we needed to use the hypotenuse that I called d of t, right? So find relationships or equations, and I'm going to just put as the last step something vague. Solve, right? This usually requires a lot of things. For one, derivatives, right? We're looking for a rate. If we found a relationship with the functions, we'll take derivatives to get to the rates. We might have to, like, I'm just going to say go back, meaning exactly what happened to us in this problem. We realized, oh, I named a bunch of stuff in the beginning, but I didn't name the hypotenuse because I didn't know I needed it. Now I need it, I'm going to name it and try to understand how it fits in, right? So I had to go back and introduce notation, go back and find a new relationship, take a derivative of that. But in some set of steps, we're going to solve it using derivatives, some algebra, and possibly going back to introduce notation, understanding something else about it. And there's often this idea that we're looking at a particular moment of time, right? Because we know derivatives and rates change. So we might not be able to say find the rate for all time, but we want to know what it is at one moment in time. And that was what we did at the end here, where we realized we were looking at the moment where h of t was 45. The height was 45 meters. And so now we could finish the problem. All right, that's the idea of related rates. Let's take this same situation and solve something else about it. Now you can imagine if this camera is trained on the drone, that it's trained on it because it wants to film it or see it, which means it needs it to be in focus. And so it might need to know, who's ever operating the camera might need to know, just moving the drawing down here. Oh, I don't need the text anymore. Let's see if we can get rid of that. They might need to know how that distance is changing, right? The focus of the camera depends on how long the distance d of t, right? So let's find how fast is d of t changing at this same moment when h of t is equal to 45 meters, right? So we don't have to do as much work this time because we've already set up the problem. So in other words, we're looking for d prime of t. This isn't entirely accurate. It's at, maybe I'll call it t1. This is the moment in time where the height is 45 meters. Okay, so d of t or d prime of t implies the derivative as a function, but we're looking for it at one particular point, the derivative at a point. So we've got notation introduced. We've got the same picture. We already understand it, but now we want to know about d prime. We still know h prime of t, or dh dt, is 2 meters per second. Okay, so this again is the rate we're going to need to use to get to d prime of t. And a good way to relate them, again, we're looking at triangles. We don't have angles this time. Another thing that jumps into our head when we see triangles is the Pythagorean theorem. We already used it before. We realized that d of t squared is equal to 30 squared plus h of t. Let's make this more clear, squared. All right, there's a relationship between the quantities we have and the quantities we want. The function that we have, or at least that we have its derivative, and the functions whose derivative we want. So we'll do the same thing we did last time. Let's take a derivative. We always apply the derivative on the left, so I'm gonna move that thing over. So we'll do d dt. Here, again, we're going to use some of the skills we had from implicit differentiation, which is really just an application of the chain rule. So look at this and go, I've got d of t, a function of t, and I've put it in the square function. So I do the outside function, that 2 comes down, I leave the inside function alone, and then I multiply it by the derivative of the inside function, d prime of t. Here we've got 30 squared, that's a constant, so that goes away. Right, that's just a number. The derivative of a constant is 0. And then I've got 2h of t squared. I have the same application of the chain rule here, where we get 2h of t, h prime of t. And I can solve this equation for d prime of t, which is going to be h of t, h prime of t over d of t. Okay, so let's evaluate this at d prime of t1. Right? Remember, t1, t sub 1 is just the moment in time that the height is 45 meters. So I can put 45 meters in for this height. H prime we know is meters per second. D of t at this moment, at t1, I do not know. Right? We haven't found that yet. But we can find this pretty easily with the Pythagorean theorem. Here's another example. There's more information. I have to go back to the beginning and get the information I need, but it's pretty easy information to get. We know that d of t1 squared is equal to 30 squared plus 45 squared, right? Because at that moment, the height is 45, and we're using Pythagorean theorem. So d of t1 is the square root of 900 plus whatever 45 squared is. And I found this to be approximately, I'm rounding to the nearest whole number, 54. So I can put that in for, this is 54 meters. And so if we cancel our units, meters cancel, I've got meters per second. I can also reduce a little bit. I've got 45 over 27 meters per second, and we can reduce that to 5/3 meters per second. Okay. And there we are. That tells us how quickly that distance between the camera and the drone is changing at this moment in time, right? I expect that this rate is smaller than 2, right? The drone's going up at 2 meters per second. This distance, the horizontal distance between the camera and this d of t is made up of 2 parts: the horizontal distance and the vertical distance. The horizontal distance not changing, the vertical distance is, and so we're getting a little less speed, right? It's just the geometry of a triangle, right triangle like this. So there we have it. That is how quickly the distance is changing, okay? So these are related rates, right? There's a lot of pieces, but notice we're labeling things and keeping track of things very clearly. Drawings are gonna be crucial in tons of these problems. And so I can't emphasize enough how important drawings are typically going to be in this sort of thing. Okay, that is it for this one. Thank you, everybody. I will see you next time.